they've kind of had a change of heart, only because it's kind of like, okay, where are we getting this triangle from? It doesn't seem like it's legit. The idea is we're going to discover the reason why we're able to use that rule to make a determination of the angle separating two vectors, which is, again, a foundation of making a determination of the orthogonal relationship between two vectors. How do we know that two vectors, when you take the dot product of them, gives you if it gives you a 0, makes it orthogonal? We know that because we have a rule that says so. But where did that rule come from? Well, it came from a few different places, but this is an example of one of those places. All right, so let me actually draw this picture, because when you have a triangle, you can do lots of things with that triangle. But the question again, of course, is why do we have this triangle? So let me flip, right, flip, up, down. So that's my negative u. All right. So I need v plus negative u, so the sum of those two vectors, which again is what you would get if you were to create the corresponding parallelogram from the appropriate vectors. Undo that. Actually, lock in place. Clone. All right, so this vector here would be u, v plus negative u, which is the same, obviously, as v minus u. And so you can see that this is the same length as that one. So all I'm doing is taking a tail-to-tip approach, or tip-to-tail approach, as opposed to having it all centered at 0. All right, so this guy is going right up, yeah, and becoming that vector. All right, so that's where the triangle. Well, I did want to gloss over, but I changed my mind. So anyway, what we have here is a triangle. I can figure out angles in a triangle using SOHCAHTOA if I know it's a right triangle, but I don't know it's a right triangle. So I need other methods. If I have the area, maybe I do a little 1/2 AB sine C. I don't have the area. But as it turns out, once we learn about the cross product, we're going to figure out ways of determining areas, not necessarily exactly of triangles, but of parallelograms. And we know that if we chop a parallelogram in half by the diagonals, you actually get triangles. So if we only knew what a cross product was, maybe we can come up with the area and then use a simpler form to come up with that particular angle. But we don't have that. So you start thinking of other things like the law of sines. I need two angles, unless I want to get into the ambiguous case, which I don't, or the law of cosines. All right, so let's take a look at the law of cosines. Doesn't really matter which variation. C squared I'll go with is equal to a squared plus b squared minus 2ab cosine of c. All right, so I'll just label this up. I'll call this C, A, B. You can pretty much label it, well, I don't want to say any way you want, any way with the condition that C has to be where angle theta is. All right, so you really have two possibilities. So side C, we don't just say it's V minus U, because V minus U is the difference between two vectors. Right? It's not an actual distance. But if I throw a little magnitude on those bad boys, it would be. So v minus u squared is equal to, I'm just turning it off. V squared plus side B, which is my u as a magnitude, bless you, minus 2ab cosine c. So minus 2, side A is magnitude of v, side B is magnitude of u, times the cosine of c. So I got to sneak it in. So cosine of the angle at C, which is theta. All right, so like I said before I left the room, we could always square out a magnitude, but you can't do it in a way that you would normally expect. All right, so the magnitude squared is equivalent to the dot product of the two corresponding vectors. All right, multiply. And the two corresponding vectors themselves are the same, so it's basically a binomial squared, but by the dot product. Now, it's a dot product of a variable expression, so we just have to be a little careful with this. All right, so v minus u dotted against v minus u. So the algebraic operations distributive property is something we talked about, I think, on the previous page where I said it still holds. So everything that we do with the distributive property with the dot product is still going to be the same, at least algebraically, or at least in the early going as it would be in an algebraic expression, except the multiplication connectors are as a dot product. So we have to keep that in mind. All right, so we're looking at v dot v. The outers, well, it's binomial squared, so we're looking at a u dot v and then another u dot v. So minus 2 of those u dot v's. Plus u dot u. All right. Now, relationship here is a property. I know. If this is your first rodeo with this stuff, you're like, it's a property you just learned like 20 minutes ago. So how would you be expected to know it? Well, I don't know. Put it on an index card, I guess. But for those of you who have seen this before, I guess you have a slight advantage there because you may know this like the back of your hand. Although I don't expect that that's necessarily the case either. I think that properties are the kind of things where people are like, all right, yeah, they're there, they're useful. You don't really think about them because they don't always come up, and so they kind of go by the wayside. But this is an important one in this case because v dot v is the same as the magnitude of v as a quantity squared. And same thing with the u's. Magnitude of u squared. Now, it may not look like it, but we're pretty much there. We have the proof. Because On the left-hand side, we're looking at the expansion of the magnitude of v minus u squared. The right-hand side is all this stuff. Right? So if I were to rewrite all this, and I'll do it below, just to kind of make it look a little nicer. We have v squared magnitude minus 2 times the dot product. Get all that stuff. All I did was rewrite the left-hand side equal to the right-hand side. But it becomes very clear, hopefully, that we have a common magnitude of v squared on both sides and a common magnitude of u squared on both sides. Those are going to cancel. Right? Those are numerical values, or scalars, so they go away. Rewrite. Now we have a constant multiple of -2 on both sides. Those will cancel. Multiplication is commutative, so these two can switcherooski. And we have u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. Okay, so that's where the rule comes from, at least in the rule that generates the angle. And all it is really just taking two vectors and creating a triangle out of them. But the measure of the third side of the triangle is the difference between the two vectors. It doesn't look like it would be the difference because, you know, geometrically it doesn't feel right. Like, how is that v minus u? If I take some vector v and subtract from it vector u, how is that going to give me that particular vector? It doesn't feel right, but it is. Right? And so that encloses the triangle. Trigonometry helps us get the rest of the way. Right, but still, we haven't really talked about what a dot product is. It's really just all different ways of getting to a dot product. We haven't really gotten to the heart of it. And in all honesty, kind of beaten it to death. You might not even be remotely interested in what it is. I know I wasn't as a student, but became more and more interested as I got further into the teaching field. Like, what is it? What is it? It's 2. It's 0. It's 20. What is it conceptually? So, let me draw two vectors. I'll keep it relatively simple. One horizontal. All right. So, what it actually is the product comprise of a vector and the component of another vector acting in the same direction. All right, so I have vector, we'll call this u, and we'll call that one v. So what we'd be looking at here is the product of the magnitude of vector v and the part of vector u, the magnitude of that is also in the direction of v. All right, because you got to figure that there are horizontal and vertical components that make up this particular vector. Okay, so it's just a question of, well, what are those horizontal and vertical components? All right, so what we do is we drop an altitude. We'll call this u sub v. Right, so it's not a rotation of vector u. Okay? That's a common misconception. It's like, if I just rotate this vector down and just kind of smush it onto vector v, then that would be the part that's getting multiplied. Well, I mean, you could try that. It's not going to work. But what we're doing is we're taking, if you look at the horizontal and vertical components with projectile motion, if you have any experience with that, it kind of makes a little bit more sense, because if you throw something up in the air, you have a horizontal speed, a vertical speed, and they both have different interactions that causes the object to take the shape that it does. Right? So if you wanted to figure out where it landed, then you would determine when the height is equal to 0. If you wanted to figure out how fast it was going when it landed horizontally, you would take the moment when it landed vertically and just plug that into your horizontal equation, then maybe do some derivatives or average rates. But you know, there is that interaction between the horizontal and the vertical. Now you expand it into 3 dimensions, and you have different components that come into play, because maybe it's going on a plane that isn't quite vertical. You know, if it's going on an angle, like I was kind of likened it to I mean, I know it's not the same because friction's involved, but when I wanted to get silly with a frisbee, like instead of just throwing it straight, I would throw it up towards the right, just kind of pitch it up to the right, and it would create that angular movement. That's a new plane that frisbee is traveling on, right? And you know, friction throws everything out of whack, but now there's new rules, because it isn't just a vertical and horizontal component. There's an oblique component now, so that changes everything up. But if you know what plane it's living on, then you could start to make some judgments based on the interaction between the 2 vectors. All right. So if you and it's a linear transformation, because what you're doing is you're taking this, if you extend this line infinitely, you're taking points and just dropping it down onto whatever line you want it to drop down onto. So if I were to extend this on, because vectors can be infinite, if I have some sort of incrementation, each one would create a vertical, in this case, because I established this horizontal. So I would be creating altitudes, and each of these altitudes would be equally spaced. Okay? So by maintaining my equal spacing, I'm establishing something as a linear transformation. But what we're doing is we're taking a transformation from 2 dimensions into 1 dimension. So that's pretty interesting, because if I had something that, for example, followed a parabolic arch, the spacing would not necessarily be consistent. I mean, depending on what portion of the parabola you're on, it might be. But once you get closer and closer to the vertex, things start, it starts getting closer and closer to 0 spacing. So you would not have something that's a linear transformation, because when you drop, if you develop increments along that parabola, so if I have my curve here, I establish equivalent arc lengths along that parabola, it would not necessarily correspond to equal incrementation along this line. All right? But with linear transformations, it does, so it's kind of cool in that regard. But anyway, what we're doing is we're basically taking the end of my vector and then just shooting it down so that it becomes a 2-dimension to 1-dimension linear transformation. All right, and we'll get to how that actually is accomplished down the line. It's just basically multiplying by the appropriate matrix to get you there. Because if you think about it, if you take we did a 2x2 matrix multiplied by a 2x1 matrix. That gave you a result that was a 2x1 matrix. So a vector in 2 space. You maintain the space. But if you can establish a transformation matrix that would bring you down a dimension, so maybe from a 3-dimensional vector to a 2-dimensional vector, then you would have basically accomplished what I'm talking about. Anyway, you have an angle that's separating these two guys. We know trig for the most part. Cosine of theta is equal to adjacent over hypotenuse I don't want to get into the, in Calc 3 we use projection and component notation, PROJ, COMP. I think that's a little overkill because we're not going to go too crazy with this stuff. It's more for theoretical. So if we just know that U sub V represents vector U in the direction of V, then that's good enough. All right. So what that tells me is that U sub V would be equal to U times the cosine of theta. All right. Now, what is really U? I mean, I've designated them as U and U sub V, but they're really magnitudes, right? Because I can't do a mathematical operation the way I've illustrated it here without actually having numerical values. All right. So the dot product, again, is defined as the vector, the product of the vector, and the component of another vector acting in the same direction. So here's my other vector, U. I want the component, I want the part of it that is acting in the same direction as V, multiplied by the magnitude of V. All right, so this is basically telling me that the dot product of U and V would be equal to the magnitude of U sub V and U cosine theta. Oh, I'm sorry, V. That's weird. Right, this is the component that's acting in the same direction as V, and this is the magnitude of V itself. And we know that the component that's acting in the direction of V is known as U cosine theta. There's my V, and so there we have it. I think this definition, or at least this proof, this approach to developing the dot product formula, tells a little bit better of a story than the law of cosines one. Because the law of cosines one will tell you how you come up with a formula for finding the angle between two vectors, but it doesn't really ever tell you what a dot product is. And this one, I think, does a better job of that. I like them both. Because anytime I can incorporate trig into anything, I like it a lot. Oh, I had a moment of pause here, because when I hovered over this, Well, it said 0 on there, and I thought it wasn't running, but it was.